Welcome to AP Chemistry at Honolulu High School. I'm Brian Brown, and today we will be looking at the detailed solutions for the activities related to acid-base equilibrium that we did in class. Okay, first question. This is one that I've seen a number of different times, and it's always confusing to students because they're not really sure where to start. Well, remember, molarity is a mole per liter amount. So if we had something like, let's say, the density of water, which you know is 1 gram per milliliter, then you can convert grams to moles and you can convert milliliters to liters and you can find out what the density of water is. So that's really all you're doing in this particular problem. So what we really need to do here is convert that thing on top to moles and the thing on bottom, that unit, to liters. So if we've got 1 gram per milliliter, that would be 1,000 grams for every 1,000 milliliters, which is literally then 1,000 grams per liter. So all we really have left here is to find out, and that'd be 1 liter, in 1,000 grams, how many moles do we have? So in this particular case, 1,000 grams of H2O. And we know the molar mass of water is 18.0 grams per mole. If we do the math, we end up with, when we divide that by the number of liters, we would end up with on top 55.6 moles. And that was in 1 liter, so that's 55.6 molar. So water is technically a 55.6 molarity. Okay, second question. What is the pH and the POH and the H3O plus and the OH minus of each? Now this is really dealing with understanding if you've got strong acids and bases, how they dissociate, and then how you convert those into p-values and vice versa. So if we have HCl, it's a strong acid. Remember, you got to memorize your 8 strong acids and 7 strong bases. We know this dissociates 100% into H plus. So if it's 0.0010 molar HCl, it's also 0.0010 molar H plus. And if we take the negative log of the H plus, we get the pH. So in this particular case, taking the negative log of that, we would get 3.00. Remember how sig figs work? Two significant digits goes to a p-value with 2 decimal places. Now, if we know the H plus and the pH, we're halfway home on this one, because remember H plus is the same as H3O plus. To get POH, all we really have to do is take the uh, pH, which is plus POH, would have to add up to 14. So 14 minus 3.00 would give us a POH of 11.00. So now we have POH as well. And finally, all we need is OH minus. Well, if we take the 10 to the negative 11.00, we would get 1.0 times 10 to the negative 11th. That would equal our OH minus concentration. So there are our 4 values for the first one. So if it's a strong acid, strong monoprotic acid, we know the concentration of the acid equals the concentration of the hydronium. And from there, we could figure all the rest out. Now we have a strong base. If it was a monobasic, a 1-hydroxide strong base, the same thing would apply. But in this particular case, we've got a 2 here. So if it's 0.25 molar BaOH2, that would be an OH minus concentration of double that, which would equal 0.50 molar. So that's our OH minus. Now, if we take the negative log of that, we would have the POH, which in this particular case is going to equal 0.30. Remember, 2 sig figs, 2 decimal places is a p-value. So now we have OH minus and POH. Well, if I know my POH is 0.30, 14 minus that would give me a pH of 13.70. So remember, it's just 14 minus 0.30. And if I take 10 to the negative 13.70, I would have the H plus or H3O plus concentration, which in this particular case is going to equal 2.0 times 10 to the negative 14th molar. So those would be my four values for OH minus. So the big thing is when you have a strong base, watch the formula. In this case, stoichiometry would dictate I get twice as much hydroxide as with a monoprotic strong acid type situation or a monobasic base type situation. And once you know one, you need to be able to convert to the rest. Okay, next day we looked at our K problems. So whenever you have one of these equilibrium problems, the first thing you should always do is write down your reaction. So I have lactic acid, which is C3H5O3. I'm going to write the hydrolysis for that in water. So what happens when I put it in water? Well, as an acid, it's going to give a proton to H2O, making H3O plus, and what I'm going to be left with is the conjugate base of that substance, which would be C3H5O3 minus. So that would be the dissociation reaction that we're looking at. Now, the next thing we typically do in one of these problems is we'd set up icebox. And I'm going to go ahead and do that for this one, although in many situations, once we get a handle on it, we don't really need to set up the icebox. For this one, I want to take a look at what I'm given and plug it in where it's appropriate. So it says in a 0.100 molar aqueous solution, so I know this is 0.100 molar aqueous solution, and it says it's 3.7% disassociated. So that means this number right here is going to go down by 3.7%. So what I really need to do is take 3.7%, which would be 0.037, and I multiply that times my concentration, which is 0.100, and that would tell me that my concentration dropped by 0.0037. So 3.7% of 0.100 is 0.0037. So I know in this particular case, at the beginning here, these are going to be 0. So we started with this concentration. We just found out it's going down by 0.0037. And by the stoichiometry here, this is a 1-to-1-to-1 equation. That means both of my product concentrations have to be going up by 0.0037. Which then gives me my equilibrium concentrations. I know this is going to end up at 0.1 or 0.0963, and I know both of these are going to be 0.0037. And the question was, calculate the K for this acid. Well, we always start with the equilibrium expression. So the equilibrium expression in this case would be the concentration of H3O plus times the concentration of C3H5O3 minus all over the concentration of our acid, which is HC3H5O3. Remember, those are equilibrium conditions for all those, which in my icebox setup here, I just determined what all my equilibrium are, so I can plug those in. On top, I'm going to have 0.0037 times itself, so that's squared all over 0.0963. So remember, really the key to this problem was right there. That tells me how much my reactant went down and how much my products are going up. At that point, I know my equilibrium concentrations. I can plug in, I can solve for the K, which to 2 sig figs ends up 1.4 times 10 to the negative fourth. And remember, we have no units for the K. So that would be the answer for question number 1. Now, question number 2 is a more typical Ka problem. In the last one, they were asking us to find K. Notice in this one, they're giving us a K. So this is going to be one of those problems we saw numerous times in the chapter involving X's when we set up our icebox. So hypochlorite ion is a strong oxidizing agent also often found in household bleaches and disinfectants. It is also the active ingredient that forms when swimming pool water is treated with chlorine. In addition to its oxidizing ability, the hypochlorite ion has a relatively high affinity for protons, so it's a much stronger base than Cl- and forms the weakly acidic hypochlorous acid. So we're going to write the dissociation equation, and we're going to write the hydrolysis form for HOCl. So when we take HOCl and we put it in water as a weak acid, because it's not one of our strongs, I need a double arrow, and that's going to form H3O plus and the conjugate OCl minus. So that will be our dissociation reaction. Now, I usually write them as hydrolysis reactions, but it's also acceptable when you do one of these, and I want to at least write it once, to write it as an ionization reaction, because it's also true that this would ionize into H plus and OCl minus, and both of these are really the same exact reaction. So both these are working the same thing, and honestly, if you set up equilibrium expression, they're going to give us the exact same equilibrium and Ka expression. Okay, now we're moving on to B. It says calculate the pH of a 0.100 molar aqueous solution. Now, normally what I do is I'd write my reaction. Well, I've got my reaction right there. So I'm going to set this one up as an icebox situation. And we're just going to use the reaction above so I don't have to write it again. We know at the beginning it says we have 0.100 molar. Now, this makes absolutely no difference since it's a liquid, so we're going to ignore all of those. And on the product side, before it reaches equilibrium, I have 0 of those. So this is going to go down by x, and these are both going to go up by x. So I end up with 0.100 minus x as my acid concentration. My hydronium would be x, and my OCl minus would be x. So that's what I'm going to get from my icebox expression. Next thing we always do is we set up our equilibrium expression, which in this case would be H3O plus on top times OCl minus. And remember, do not forget to write this equilibrium expression when you're doing this on the AP test, because this is always going to be worth a point. So get in the habit of always writing it down. So that would be my Ka expression for this reaction. And I know the Ka is going to equal what's on top times each other, so that's x squared over 0.100 minus x. And given in the problem, the Ka for this particular acid was 3.5 times 10 to the negative 8. Now, this technically means we're going to end up with a quadratic equation. But if you recall from homework, the way to simplify this process is we can assume this x right here is very small compared to 0.1. So what we're going to do is we're going to neglect x. And what that means is we pretend that that's so small, it might as well be 0. And now we don't have the quadratic equation. So when I set this up and take the square root of 3.5 times 10 to the negative 18th times 0.1, that will give me what my value for x is. In this particular case, that ends up being, when I plug them in, 5.9 times 10 to the negative fifth. And remember, that is going to equal my H3O plus concentration as well as my OCl minus concentration. So that's really what X stands for in this case. Now, we pretended that X was so small that it might as well be 0. Well, you always, always, always need to double check that. And that's actually what we're going to do in the next problem. So before we go through and show that solution, let me just finish this. If this was a valid neglects x, this is my H3O plus concentration. If I take the negative log of that, 2 sig figs, I'm going to get 4.3 as my pH. So since I know from the next problem that this is going to be a valid neglect x, I'm going to go ahead and finish that and say that's 4.23. Now, how did I know my neglect x was valid? Well, this is something you always need to check, and that's checking your percent ionization. Since I know that my x value, my H3O plus, was 5.9 times 10 to the negative fifth, in any or calculation of percent, it's part over whole times 100. Well, this is the part I'm looking at. What the whole was the 0.100. Remember, that's what it could have been as a maximum possible if 0% of it disassociated. Divide and multiply by 100, and I would calculate what my percent ionization is. In this particular case, that's going to be 0.059%. Well, that is clearly less than 5%. So that means neglect X was a valid idea, and therefore I could avoid the quadratic equation. So the percent ionization in this case was 0.059%, which is very low. That's well below 5%, so I know neglect X was a valid simplification of the problem. Remember, if this would have been greater than 5%, I would have had to gone back in and done either the quadratic or successive approximations. Okay, next day we got into base situations. So what is the pH of a 0.42 molar solution of NO2 minus? Now, like everything in this chapter, the very first thing you need to do is determine what the hydrolysis reaction is. So we've got NO2 minus, we're throwing that in water. This is an equilibrium reaction. Now, since this is a negatively charged ion, we're going to pull a proton off of the water. So we're going to end up forming HNO2, and what's left is OH minus. So that would be the hydrolysis reaction for this substance thrown in water. And that's why this thing is a weak base, is it's going to make the water basic. Now, it also asks us to write the hydrolysis reaction for HNO2 minus, or I'm sorry, for HNO2, so nitrous acid. Well, if I throw nitrous acid in water, what's going to happen here is nitrous acid is going to give us this hydrogen, and we're going to form H3O plus out of the water, and we're going to be left with the conjugate base of NO2 minus. So that would be the hydrolysis for HNO2. Now it says, find the K blank for the HNO2 reaction. Well, notice I was making H3O plus, and this is an acid. So what it's really asking me for is, what is the Ka of this particular weak acid? So that's really what I'm looking at here is the Ka. Well, notice it says use Appendix D to find the Ka for HNO2. So I look up that substance in Appendix D, and all I'm really doing here is copying. It says the Ka for HNO2 in that appendix is 4.5 times 10 to the negative fourth. So remember, I'm pulling this right out of the table. So the Ka for HNO2 is 4.5 times 10 to the negative fourth. Now it says find the K blank for the NO2 minus reaction. Well, I know that was a base reaction, so we're going to call that Kb. The problem is if I look up in Appendix D, NO2 minus, I don't find any K values for it, Ka let alone Kb. So how am I supposed to determine this? Well, remember, Ka times Kb equals Kw. So if you have the Ka for an acid and multiply it times the Kb of its conjugate base, you always equal 1 times 10 to the negative 14th. So this is an acid, and this is its conjugate base. So I can find the Kb of the top reaction using the Kb of the second one. I just need to take 1 times 10 to the negative 14th and divide it by 4.5 times 10 to the negative fourth. Remember, that's really 1.0 times 10 to the negative 14th. So using that relationship, I can determine that my Kb for the top reaction is 2.22 times 10 to the negative 11th. Now you'll notice here I didn't round to correct significant digits because I bet I'm very, very soon going to be using that value. And I want to wait until rounding at the end. So if I had to report this, I would say it's 2.2 times 10 to the negative 11th. And if I'm going to use it in a previous problem, I want to keep extra significant digits there, which is where I'm going next. It says solve for x is what I should do next. So if I want to answer the question, the next step in the process is really setting up my icebox situation. Now, my reaction that we're looking at here was the NO2 minus reaction. So let me recopy this so we have it right in front of us here. And that's going to make HNO2, and that's going to make OH minus. So we know we're talking about a Kb reaction here. Now, this was 0.42 molar. So that's what I'm starting with. Water's a liquid, so we ignore that. And that's going to ionize into these two things, but at the beginning, initially, I have nothing there. This is going to go down by x. By the stoichiometry, these are both going to go up by x. So when I set up my Kb expression, I'm going to get HNO2 concentration, O2. Let me fix that so it's not confusing. The concentration of HNO2 times the concentration of OH minus all over the concentration of NO2 minus. Remember, always write your reaction and your K expression. Now, I know that's going to equal the Kb that I determined up here. So I know that has to equal 2.22 times 10 to the negative 11th. But I don't know what my x is here. So if you take a look in icebox, that's my I, that's my C. Well, what would my E be? Well, this is going to be 0.42 minus x, and these are both going to be x. So in Icebox, what I'm left with is x squared over 0.42 minus x. So if I want to solve for x, just like I talked about before, the first thing I should do is neglect x here. So I'm going to assume that's so small it won't affect the value when I subtract it from 0.42. And that allows me to avoid the quadratic equation. And when I plug my numbers in, I end up getting x is going to equal 3.055 times 10 to the negative sixth. Now, before I move forward, I have to double check. Does this ionize less than 5%? Well, this is what I just calculated, and it was 0.42 molar. When I take and multiply and divide, I get a number significantly less than 0, or less than 5%. So I know this was a valid neglect x situation, and therefore x really does equal that value. And remember, in this particular case, x equals OH minus. In a base reaction, remember, we don't get H plus, we get OH minus. So that is my valid x. Now, to finish the problem off, they ask me what is the pH. Well, if I know that's my OH minus, I can take the negative log of that value. So 3.055 times 10 to the negative 6. And I can calculate pOH. So when I do that calculation, I get 5.51. So pH would equal 14 minus the 5.51. So in this particular case, I know pH equals 8.49, which makes sense because remember at the beginning we said that NO2 minus was a weak base and this is a KB reaction, so we would expect to see a pH greater than 7. So that makes sense. Next day, we got into looking at salts and how ionic compounds, and that's the salt that I'm referring to here, when thrown into water can also affect the pH of water in some situations. So the first thing we're supposed to do here is predict whether an aqueous solution of each of the following salts will be acidic, basic, or neutral. And if it's not neutral, we're supposed to write the hydrolysis reaction. A very important thing to be able to do here for the AP test. Now the key to this is identifying what the things come from, because if it's an anion or cation that comes from the conjugate, or that is the conjugate of a strong base, it's negligible in acid-base behavior. So sodium, well, that comes from NaOH, which is a strong base. So this is the conjugate of a strong. So it's going to be negligible in acid-base behavior. Now, NO2, well, that would come from HNO2. And while that looks sort of like a strong acid, that would be HNO3, not HNO2. So this is an active ion. So NO2 minus is really an active ion. And when I throw that in water, it's going to cause the water to hydrolyze. So I should be able to write the acid-base reaction here and determine whether this thing is going to be acidic or basic. Now, honestly, you should already know based upon the discussion we talked about in notes. If it's not from a conjugate of a strong acid or base, then it's going to be an active ion. And active anions always make it basic. Well, why? Well, remember, one way we looked at this is think of water as H plus with a OH minus. Which one of those is that NO2 minus going to be attracted to? Well, it's going to be attracted to the hydrogen. So it's going to pull a proton from water, making HNO2 and leaving OH minus. That's why this thing is basic. So you should be able to know before you do the hydrolysis reaction that it's basic. But there's your proof. So if on the test, on the AP test, it asks you to justify why a certain ion is acidic or basic, remember, write the hydrolysis reaction. Okay, next one, same thing. Rb comes from rubidium hydroxide. Rubidium hydroxide, is that a strong or a weak situation? Well, rubidium hydroxide is one of our strong bases. Remember group 1 and heavy group 2? So that's not going to be an active ion. So what we're left with is ClO3 minus. Well, ClO3 minus comes from HClO3. Well, that is one of our strong acids. So this comes from a strong base. This comes from a strong acid. Neither one of these things is going to be active. So I know this thing is going to be neutral, pH 7. So the one up above, that came from a strong base, so we ignored it. And that came from a weak acid, so we couldn't ignore it. Here they both came from strongs, so we could ignore it. Next one, copper sulfate. Well, copper comes from copper hydroxide. That's not from a strong. That's from a weak base, so we can't ignore that one. That's got to be active. And then we get sulfate. Well, that comes from sulfuric acid, H2SO4. That comes from a strong acid. So we know that's one that we can ignore. So this case, it's going to be the copper cation, and since it was with sulfate, which is a 2 minus, I know this is copper 2, so it's C with the 2 plus chart. Now once again, I should know before I write my hydrolysis whether this is acidic or basic, but I want to make sure that you understand the proof and you're not influenced by what you see. So this is a 2 plus. Which of these is it going to be attracted to? Well, in this case, the OH minus up there. And since it's a plus 2 charge, it's going to pull 2 of those. Well, the only way we can get 2 hydroxides is if we had 2 waters. So we know there's going to be a 2 there. And what we're going to be left with is the H plus from both of those waters, and that's going to be 2 H pluses. So that would be a hydrolysis reaction, and because we're making H plus, you know, and that should confirm what you're thinking in your head, that this would be an acidic solution. Your pH should be less than 7. Now, what would those look like as an acid-base problem? Well, this is the reasoning you got to go through here. So if it says calculate the pH of a 0.10 molar ammonium chloride solution, and then it gives me a Kb for NH3, in order to calculate that pH, I have to go through and think about a few things. First, I need to determine the active ion. Now remember I had ammonium chloride, and I know chloride comes from HCl. That's a strong acid, so that's going to be negligible from acid-base behavior. But ammonium hydroxide is not one of my strong bases. So this is going to be my active ion. So determine the active ion, well, that's going to be NH4 plus. And since this is a cation we're talking about, we just looked at that up above, cation meant it was acidic. So this is going to be acidic. Next, write the hydrolysis reaction for this. Well, we're going to be able to prove that this is acidic. So when we add that to H2O in my hydrolysis reaction, I'm going to pull a hydroxide from water, and I want to write this like that for a second here. And that hydroxide left the water, so we're going to be left with OH minus. So that would be one way to write the hydrolysis reaction that occurs. But you need to understand that this is not the only way to write what's happening here, because NH4 can give up a hydrogen, and therefore that hydrogen can go to the water. Oops, I need to back up here. I need to totally back up and start that reaction over. Then look closely at what I was doing here. So my active ion is NH4 plus. So yes, that is true. And that's going into water, which is H2O. But since this is a substance that can donate a proton, the first way I want to look at this is the easier way to look at this. So I've got an H plus and it's going from here to there. So I'm going to be left with NH3. And when I stick a hydrogen from this acid, I'm going to get H3O plus. So therefore you can see that it's acidic. Now, there is another way to do this and write this. So that's not the only acceptable answer for what's happening here. So let's go back to what I was starting to look at before. Now in this particular case, I can pull a hydroxide from the water and stick it with that. And I can write this as NH4OH. And since I pulled an OH from water, I'd be left with an H plus, which also shows it as an acidic situation. Now, how come the top one here, this one, is how I prefer to write this? Well, because this is an unstable substance, and it literally breaks apart into NH3, and that means we are also going to have water coming off. So it's going to form NH3 plus water. And we also had that there. So really what you end up with here is NH3 and H3O plus. So this bottom situation is really the exact same as the top situation. We can write either of them and they would be perfectly acceptable. I just think it's easier to see what we're doing and to relate it to our K value here for the base NH3 or NH3 by looking at it as that reaction. So either one of these is an acceptable way to write it, but this is, I think, a little bit easier to see to do the solution of the problem. Now, since this is an acid reaction, we know what we're talking about here is a Ka. So we're trying to find a Ka. Now, how do we find that appropriate K value, which in this case we know is Ka? Well, if you look at the very beginning of the problem, it says right here, the Kb for ammonia, and now you can see ammonia NH3 right there, was 1.8 times 10 to the negative fifth. So remember, the Ka is going to equal Kw divided by the Kb of its conjugate. Well, the Ka of NH4 plus, the conjugate would be NH3. So it would equal 1.0 times 10 to the negative 14th divided by my conjugate, which is ammonia, 1.8 times 10 to the negative fifth Kb value. And that would give me a Ka of 5.6 times 10 to the negative 10th. So writing the reaction in this way really made it easier to see that my Kb value dealt with ammonia NH3. If I wrote it as NH4OH, and I didn't know it breaks apart into water and ammonia, that'd be a little bit trickier to see at this point. So we're going to find a Ka, and that would be the Ka. So technically, all this I wrote right here, that goes into that space right there. Next, I'm ready to solve for x. Now, I've been doing this long enough that I know when I write my equation, and here was my equation right here, that's what I'm going to base my K expression on. So when I solve for x here, my K expression, which is going to be a Kb, is going to equal the concentration of NH3 times H3O plus all over NH4 plus. And I know from the previous problem that the Kb is going to equal 5.6 times 10 to the negative 10th. And hopefully I've done enough of these to realize, well, these are both going to be x, and this is going to be, let me go back up to the top again, my concentration was 0.10 molar. So this is going to be 0.10 minus x. So skipping ahead here, this is going to be an x squared over 0.10 minus x, and I'm going to neglect x. And when I do that, I end up with x equaling 7, and this is, remember, my H3O plus, which I'm going to quickly write as H plus. It's going to equal 7.46 times 10 to the negative 6 molar. Now, before I go on, I need to evaluate. Was this a valid neglect x? Well, that divided by the concentration 0.1 times 100, that's going to be significantly less than 5%. So I know this was a valid neglect x situation, and therefore this is my H3O plus concentration. So if I take the negative log of that, so negative log of 7.46 times 10 to the negative 6, that is going to be my pH, which in this particular case ends up 5.13 to 2 decimal places. Okay, the very last thing we looked at, and remember this is not something that's technically on the test, but it is something you should know for college chemistry, is when we have a polyprotic situation. And like I said in class when we did this and we looked at it, I picked the polyprotic situation so we could do some useful review for the test. At the same time, we're learning how to handle a polyprotic. Well, you always start by writing your reaction. Now, this case, I'm going to do it as an ionization because I didn't want as much garbage here, so I'm not going to do hydrolysis for this, so I'm just doing ionization. Now, since H2SO4 is a strong acid, its first ionization as a strong will be a single arrow situation. This is not equilibrium, and this is going to break apart into HSO4 minus. Now, I knew this was 0.18 molar, and I know this breaks apart 100%, so I know that is going to be 0.18 molar, and I know that is going to be 0.18 molar. Now, at this point, you'd normally be done, and you'd take the negative log of that H plus, and you would calculate what your pH is. But here's the problem. HSO4 minus is a weak acid, which will itself ionize, now in an equilibrium situation, into H plus. So we're going to get more H plus and SO42 minus. And I really need to evaluate what this is going to be to find out what my overall H plus is going to be. So I know that my HSO4 minus from the previous problem was 0.18 molar. And I know my H plus was 0.18 molar. And before this thing dissociates, I'm going to have 0 of that. So obviously it's going to shift to the right, which is this down x, this is up x, and this is up x. And therefore, at equilibrium, this will be 0.18 minus x. This will be x, and this will be x. Now, when you look at the K expression, and this is an acid here, so I'm going to write Ka for this reaction, it's going to be H plus times SO4 2 minus all over the concentration of HSO4 minus. And I know that that is going to equal x squared over 0.18 minus, oops, that's not x squared. Remember when I do my E here, so this is my I, C, and E, my equilibrium, it's 0.18 plus x. So let me fix that real quick. At equilibrium, I know what's on top is 0.18 plus x times x. And on the bottom, I'm going to have 0.18 minus x. Now, this all has to equal my k. So where do I get my k for this substance from? Well, if I look it up in the back of the book in Appendix D, I don't find HSO4 minus there. But I do know that it's the second ionization of H2SO4. So if I look up the Ka2 of H2SO4, that's going to equal the Ka of this substance. And that is 1.2 times 10 to the negative second. Now, here's where we run into some issues here. Normally what we would do is we would take this right here, and we would do our neglect x. In this case, I've got two x's I would try and neglect. The problem is when I calculate what the value for x is, when I do that, and I check my percent ionization, I'm greater than 5% ionization. So neglect x is not a valid shortcut here. I can't do my neglect x. So literally, I'm going to be stuck with a quadratic equation for this one. So what you have to do is algebraically manipulate this out. 0.1x plus x squared over 0.18 minus x. Multiply that by the other side. And after the result of all of my algebra here, I'm going to be left with x squared plus 0.192. Make that look more like, yeah, need to draw it right the first time. X squared plus 0.192x minus 0.00216 equals 0. So this would be my A1, my B, 0.192, and my C, negative 0.00216. And when I plug that into the quadratic equation and solve for x, the quadratic equation says x equals 0.01066. Notice once again, since I'm not getting my final answer yet, I'm keeping extra significant digits. So through the quadratic equation, that is what x equals. Now remember, my question was, what is my H plus concentration equal? And that was my H plus. It was 0.18 plus X. So I had 0.18, and I just calculated that went up 0.01066. So what my actual concentration is going to be is 0.19066 molar. Now if I take the negative log of that, so the negative log of this value, I end up with a pH of 0.72, and that's my final answer. So it's a little bit more involved here. First, we had to figure out what was happening with the strong, and then we had to pull those concentrations down and do an equilibrium problem. So honestly, if this was a triprotic acid, we would have to go one more step. Now, keep in mind, let's take stock of what we actually found here. We know that the H2SO4 concentration, so what is the concentration of this thing? Well, that's going to go to 0 because it's a strong acid. That's going to totally disappear. My HSO4 minus would be 0.18 minus 0.9 or 1906. So I could subtract 0.01066 here, and then I would calculate this concentration. I know my SO4 2 minus is going to equal X, so I know this concentration is going to equal 0.01066, and I calculated that my H plus concentration was the value right here in the middle. So if they asked me to calculate any of those concentrations, I could find out all four of them. H2SO4, well, that's going to be 0. SO4 2 minus, that's going to be 0.01066. And then if I just add and subtract from 0.18, I can calculate my HSO4 minus and my H plus. But the actual place they asked us to go with this was what was the pH? And that finishes the solutions to the daily activities we did for chapter 16.